We're going to start today's class with a quiz, and then we're going to go on to particles in space. First, I'm going to do collisions. Then I'm going to do particles interacting with gravity, and then I'm going to do some Matlab with particles interacting with gravity. Everybody out in TV land, see if you can answer this question. This is your nightmare. Please answer this question. Okay, we have this chain of springs and blocks and dash pots and stuff all over the place. And the question is what is the tension in spring 2? This is spring 2. At the current instant, this distance is 2 centimeters, and the relaxed length of the spring is 3 centimeters. At the instant in question, this is the situation. And here are the various variables. And the question is, which of these things is right? And I'll turn on the clicker while you think about it. Do you want to do it alone or in pairs? Talk to your friends or make friends. Wrap up the vote in 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. Display. Okay, A, B, C. How did you guys vote? C. So many of you got it right. I'm not going to even discuss it unless somebody wants to ask me a question. Yes? Wouldn't it change if x2 was in the negative direction? Now, what x1 by the picture is defined in this direction? I did. This picture defines x2. x2 is the distance from here in that direction to this point. Now, if you want to get very tricky, and you put E here, because you think that I'm a tricky guy, these two of you, and you wanted to answer the question in the special case that x1 was bigger than x2, and this thing was on the other side, then you would get E. It depends on x1 and x2. So this formula does depend on this thing being like this and the spring not flipping around. Now, it actually becomes ambiguous because sometimes springs, they go through each other and it doesn't change. The spring doesn't flip around. So then it gets complicated. So were the two of you who voted for E thinking of the case where this is all the way over here? Raise your hand if yes. You were thinking that this mass was on this side? Okay, you get bonus points registering it. Okay, any other questions about this? The main point, which I've said to anybody who comes to office hours, I think I've said it in class, it's in the book, springs, all springs are always in tension all of the time. And all springs are longer than they were when they started, all of the time. The amount of that lengthening and the amount of that tension might be negative. But if you just pick that sign convention, it makes it so problems will work out for you, and the algebra of negative numbers will take the place of you're going, but it's pushing that way, but I thought it was that way, but I was pulling back, but because of action-reaction, it's the other way, but it's the opposite of that because it's the force on the other object. And Murphy's law says that the chances you're coming out of that alive are less than 50%. Okay, so you avoid that by all springs are always in tension. Any questions about that? Okay, so now I want to go on to a new topic. I'm going to do this a little bit out of order because I'm going to do some Matlab that picks up on the last class's stuff, but I want to do that at the end of lecture instead of going back and forth to Matlab. So what would naturally come next, I'm going to do third. What I'm going to do next is out of order, but hopefully you can survive that. So what we're going to talk about now is collisions in 2D or 3D. I'm only going to talk about them in 2D, but nothing is really different in 3D. So the basic problem we want to deal with is what happens when two things collide in space. And at this point, all we can deal with is balls. So you can think of balls flying through space and banging into each other, or, oops, there you go. Or you can think of billiard balls on a table. It's probably easier for you to think about billiard balls on a table, but the same idea as balls in space. And the question is, if you know the masses of the balls and how fast they're going before the collision and their geometry when they collide, can you figure out what the velocities are after the collision? That's the basic problem. So the problem goes like this. We've got two balls. Here's ball A, MA. Here's ball B, MB. And this one has some initial velocity along this line, and that we'll call VA minus. And it would go happily along like this, but for the fact that when it gets over here, it collides with, let me draw this at some angle so it doesn't look too special. It gets over here, it collides with this ball, V, which had initial velocity VB minus, and they get to this configuration and they collide, and the geometry of that collision is determined by the common tangent plane of these balls. So they collide like this, and there's a big noise, a big explosion. You heard that when those balls were banging against each other, because you zoom in with your close-up camera and your super microphone, and then when these things banged into each other, you zoom in up close, and it went like that. Okay, so there's a big explosion when they hit. And that happens right here. And then, after that explosion, they go shooting off in some other direction. And this goes shooting off in some other direction. And this we'll call the velocity of B plus. And this one I'll call the velocity of A plus. And the geometry is given by this line here. And you cannot figure that out from these velocities, because these balls, whatever their velocities were, could have hit in a tangent way one way or a tangent way another way. I don't know if your eyes are good enough for this. But these balls coming in like this could have hit with their tangent plane horizontal. They could hit with their tangent plane vertical. They could hit not any which way because the back sides can't touch each other. But the tangent plane can be, well, actually it can be any which way, because half the sphere is enough to get all tangent planes, because you get both sides. So the tangent plane can be any which way. And you can't tell that from the initial velocities. That's part of the geometry. And we'll call that NAB, which is equal to the normal to the tangent plane at the collision, to the collisional tangent plane. Okay, so the question is, if we are given a bunch of stuff, let's say we're given this mass, we're given this mass, we're given the velocities of the balls beforehand, and we're given also this NAB, the tangent plane, can we find VA plus and VB plus? So what's the way we solve a problem like this is you say, what do we know is true? We write down what is true about these things, and we see if we can say enough true things so we have enough equations, enough unknowns we can solve. So what are the kinds of things which are true? Well, we can draw free body diagrams of both balls during the collision. So these are collisional free body diagrams. And what means a collisional free body diagram is that I'm drawing this thing. I've got this tangent plane here, and here's this mass A. And instead of drawing a force here, I draw an impulse. And what is that impulse? It's equal to the impulse on A from B, and that's going to be some NAB times some P. And NAB was pointed that direction, and if I want P to be positive, which I do because I don't allow sucking collisions, just like all springs are in tension, all collisions are in compression. This is the expression I get. Now what is this P? P is the collisional impulse. The word impulse in mechanics does not necessarily mean something collisional. It just means the integral of f dt. The impulse means integral of force with respect to time. It's the change in momentum of something in one dimension. Now we have similarly the free body diagram of B. We've got the same normal plane here. Here we have NAB on the side. Here we have NAB on the side. And then we have a collisional impulse here. And this is the impulse on B from A. And what is that equal to? It's minus this one, so it's P times NAB. Now if we write linear momentum balance, and in this case it actually is linear momentum balance. It's not in the Fm equals ma world. It's the impulse momentum world. The change in momentum is equal to the impulse. We have for block A that V B times mb plus is equal to the momentum beforehand plus this impulse, and this impulse is this NAB times P. So just stare at that equation. Let's see if there are any questions. Well, let me write one more, and then I'll take questions on everything. For block B, okay, that was block B. For block A, I have the same thing. ma times velocity of A plus is equal to ma times the velocity of A minus minus n hat AB times this scalar P. Okay, now copy it down and ask questions. Or tell me mistakes I made. Questions? What? Go ahead, do it out loud. Anything you want to ask to your friend, ask it out loud, please. Go ahead, you. Go ahead, talk about it. Just talk louder, please. This one here, right. So it's true that this P is the integral of this force, which I assume I know the direction of. I could also have written PAB is equal to the integral of FAB dt. So this would have been a legitimate equation to write. I just didn't bother because we know the direction ahead of time. Does that address your question? Okay, who else was asking their neighbor a question or wanted to? Yes? Is that some extreme form of like conservation? What was it? I missed one word in that. Is that some sort of manipulated form of conservation? It's not very manipulated. It says the momentum after is the momentum before plus the impulse. If you want to know how to derive this, we could say that the mass times the acceleration is equal to the force. This is our basic equation. And therefore, if we take the mass times the acceleration integrated dt equals the integral of force dt, then we see what this says. The integral of mass times acceleration is the change in velocity. So it means the change in velocity times the mass is equal to the impulse. And this says that the mass times v2 plus minus v2 minus, sorry, v, I'll just put v plus v minus is equal to the impulse. So it says m times v plus is equal to m times v minus plus the impulse. So if you want to start from F equals ma and derive this equation, I guess you could say it's a manipulated form of conservation of momentum. You usually don't think of this as conservation of momentum, and you actually don't think of this as conservation of momentum. This is lack of conservation of momentum. This is the change in, so it's called the impulse momentum equation. Impulse momentum equation, this one is the integral of F equals ma. Does that address your question? Yeah. Okay, very good question. Any other question? Yes?
How do you know which impulse is positive and which is negative?
Okay, so we start out by, here's these things banging into each other. We assume that the interaction is a compressional interaction. So let's start out and look at this guy. The force has to end up in this direction. That direction is the same as that direction. Therefore, this PBA, the impulse on B from A, has to be in that direction if we assume this is a positive number. And this gives us this positive sign. Who asked the question? Are you happy with this one? Couldn't I define the normal this way or this way? So what I've said is this is the normal from A towards B. And then this has to be like this. And this is the force on B from A. And then this has to be the negative of it. Now, one common confusion, which you just have to get used to, is how to work with vectors and arrows. If I have a vector symbol here, which I do, then you ignore this arrow. The meaning of this vector is not anything multiplied by this arrow. It's all in this symbol. This symbol is defined by this picture. Okay, any other questions? Okay, so what do we have here? This set of equations here is how many scalar equations are written here? Little quiz question. How many scalar equations do we have? How many? Raise your hand if you think 1, 2, 3, 4, 5. More than 5. Okay, 4 is the right answer. Because if we're in 2 dimensions, if we break this into x and y components, or any 2 components we want, we get 2 scalar equations of 2 here. And then our favorite math expression we get is that 2 plus 2 is equal to 4 scalar equations. Okay? How many unknowns do we have? Back over here. Well, we wanted to find these 2 things. That's 2 unknowns each. We have 4 unknowns. So we have 4 equations and 4 unknowns. Not. What's wrong with that? Well, it's true we have 2 equations over here, and we had 4 unknowns over there. The problem is we introduced a new variable. So we actually have 5 unknowns. Now we could say, can we find another equation? What about conservation of momentum for the whole system? Well, what does that say? It says that MA VA plus MB VB plus is equal to MA VA minus plus MB VB minus. So we have 2 more equations. Not. Why isn't this 2 more equations? You answer too much. Somebody else. Yes?
It's just the addition of...
Right. If we add these 2 equations together, it gives us that one. So conservation of linear momentum for the system follows from the impulse momentum equations for each of the parts. You happy with that? Okay, so this is not independent. So we're missing some equations. Now, physically, we can think about this. Have we put on the blackboard all the things we need to know for a system like this? Well, if I had that air cart here before, remember I had that air cart? And it had the masses and the tracks, but somebody gave me a piece of gum and I stuck it under the air cart, and then 2 days later I pulled out the gum. Well, if I had that piece of gum, I could put it right here between these two, and these two could fly up with the same initial velocities and the same masses and the same normal plane and stick together. And all of these equations would apply. Yet the result is different. So I have not yet put on the blackboard something that says the difference between a bouncy collision, like these things, and a sticking collision. So I need to tell the blackboard something about whether this collision is sticky or not. And that will be our fifth equation. So we need this restitution equation. This is what they need in Texas now, right, where they're having, or Louisiana, where BP is having this big lawsuit about restitution. And they could, all they need is a restitution equation. They could solve that problem. Okay, so we need this restitution equation. Every now and then I'll tell a funny joke. That one didn't work, okay, but sometimes there'll be funny ones. Namely the ones that I don't make up. Okay, so there's the restitution equation. How does that go? We want to say whether it's bouncy or not. Well, remember, the bounciness has to do with how fast they separate compared to how fast they approach. So this is their relative velocity afterwards. And we're going to try and relate that to the relative velocity before. And the way we relate it is we say somehow the relative velocity reverses. So we put a minus e here, and this is the coefficient of restitution. And this looks kind of right, because that's kind of what we had in one dimension, but it's not right. And the reason it's not right is that, let's say the balls are moving up and down. And let's say the normal plane is more or less vertical, so they contact like this, tangentially. And if I said the velocity is reversed, I would get a collision like this, where they hit like this and they bounce back. Which obviously doesn't happen, right? The most that could happen is they start spinning, but I don't even have spinning in here, right? I'm kind of living in a particle world, even though I've drawn balls. And I also said on the board there, I didn't say anything about it, we're assuming no friction for this collision calculation. So the collision is not about reversing of tangential velocity. It's only about reversing of normal velocity. So the restitution equation doesn't have to do with how the relative velocities change. It has to do with how the component of the velocities, relative velocities, normal to the tangential plane reverses. And so what we have to put here is a dot NAB, and we have to put an NAB dot here. So this is how much the relative normal velocities reverse. And if we have E equals 1, it's what we call totally elastic. And that's total reversal, which means the normal component of the velocities reverses. And if we have E equals 0, that's called totally plastic. The word plastic comes from the word clay. Think of it as like chewing gum. And this is equal to so-called dead collision. They just stick together. Dead sticking collision. Okay, so now if we're going to number these equations, we can number this 1, 2, and 3. So now we have, what did I do wrong? This is for very small values of 1. So equations 1, 2, and 3 are 5 equations for V A plus V B plus and P. And then you solve any way you want. And it could be that we don't have this canonical problem. The canonical problem is given the past, we want to predict the future. But you can also use the same equations to predict the past. What do I mean predict the past? To determine what the past was based on a present measurement. So it could be, for example, you see a car accident, and you know what the cars did after the accident, and you have some of this information, and you try to figure out what happened before the accident. Okay. And I'm going to drop this, and you can look at examples in the book and in your homework. But any questions before I drop it? Okay. Solve any way you want. Also, use 1, 2, and 3 with different givens and unknowns. Yes?
It looks like we have 6 equations now. This number is 2. Does that mean we can solve it with 6 variables? Or is it because of the dot?
The purpose of dot is to turn vector equations into scalar equations. So that's just one equation. Yes?
In this, are we to understand that the normal vector is found?
This depends on how you want to think about it. For the canonical, simple predicting the future problem, the initial masses are given, which don't change in time. The initial velocities are given, and the geometry at the collision is given. The normal is known. But you could imagine a problem where somebody tells you the initial velocities, the final velocities, and asks you to determine the normal. So what's given and what's not depends on what information you know about the collision. Does that address your question? Okay. So now I want to change topics to do multiple particles in space. In a way, this is to set you up for my favorite homework problem all semester, which you have coming up, which is I met a guy named Montgomery at a meeting a few years ago, and he said, I found a beautiful solution to the n-body problem for n equals 3. So I don't know if you've heard this concept of the 2-body problem, the 3-body problem, the n-body problem. Nowadays, people say the 2-body problem, they mean some couple wants to get a job someplace, and they say, oh, they have a 2-body problem. But it's meant to be a pun or a joke on the famous mechanics problem, which is called the 2-body problem, which is 2 particles are flying around in space, how do they move? As opposed to the 3-body problem, where 3-body and you're trying to figure out how they move. Or the n-body problem, where n particles are moving around in space, and you want to figure out how they move. As you know, these equations get very hard to solve. There's almost no known solutions to the 3-body problem for inverse square gravity, but this guy found one, and your homework problem is to verify it on the computer. It's a beautiful thing. Okay, we want to set you up for that. So let's say we have a bunch of particles, say A, B, and C. And what's happening with these particles is that they're interacting with each other, and maybe there's some external force on A which is like that. So there's some external forces, maybe external forces on C, and so on. Let's take two of these particles. Let's look at this force right here. What we'll call that is the force on B from C. And we'll call this the force on C from B, which is equal to minus the force on B from C. And so on all the way around the picture. So if we're given, these are free body diagrams now, right? So to solve on the computer, and you really don't have much hope of solving problems like this not on the computer, those very special ones you can. Like if you're Isaac Newton and you're doing the two-body problem, you can solve that on pencil and paper. But most of us have trouble with even the two-body problem. To solve this on the computer, you just write F equals ma for each particle. So in 2 dimensions, we have a z dot equals f of z, and this would be 2n equations, 4n equations. Why 4n? Because for each particle we have x and y, and for each particle we have x dot and y dot. So z would be, for example, x1, y1, x2, y2, dot, 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 vx1, vy1, dot, 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 and down the line. And if you have room in your notes, write this as a single column vector. I'm just putting dot, dot, dot. This belongs down there. What are examples of interaction forces? Let's say the most famous one would be FBC associated with inverse square gravity. Inverse square gravity. And then we need to write this in a nice vector form so we can break it up into components nicely. FBC for inverse square gravity is the product of the masses, MB, MC, divided by the distance squared. So that's the position of C minus the position of B squared multiplied by gravity. That's the magnitude of the force. And then we need to multiply that by the direction of the force. The force on B from C is the position of C relative to B. So that would be RC minus RB divided by the magnitude of RC minus RB. So that would be an example of the force. That's inverse square gravity. And this is the famous one that Newton used to figure out the motion of the moon around the Earth and the Earth around the sun and so on. Another example would be, say, for a spring. Let's say it was a linear spring connecting these things. Then the magnitude of the force would be K, the spring constant. It would be multiplied by the change in length, which would be the magnitude of RC minus RB. That's the current length minus the initial length. That's the magnitude of the force. And we multiply it by a unit vector in the right direction. And a unit vector in the right direction, if we're looking on the force on B from C, would be this position of C minus the position of B divided by the magnitude of RC minus RB. And this would be for a linear spring with rest length equal to L0. Okay, any questions about either of those equations? Okay, any questions about anything on the blackboard? Yes? I couldn't hear a word of what you said. Right over here, I'm trying to say that if we have 3 particles here, we should have 12 equations. If we have z dot equals f of z, the z is a list of the 3 x positions, 3 y positions, 3 x velocities, 3 y velocities. So this says x1, y1, x2, y2, dot, 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 and then it's supposed to continue down here, vx1, vy1, vx2, vy2, and so on. Does that address your question? So this is just meant to be one long column vector. In this case, it would have 12 elements in it, which is a homework problem that you have to do. So you have to do that problem with this law in it. So you should understand it. Any other questions? Any quick questions about the test tonight? Not all of you are registered in Piazza. There's been some dialogue there which might be interesting to some of you. One particular thing is I posted the cover sheet for the test tonight. It will save you time and trouble if you read that now. Yes? Do you have to do the solution form of every question for the test? You mean how good should your answers be on the test? I'd say, okay, so most of the, there's probably 100 test solutions posted on the web right now. Right? There's like 10 semesters of this course, 10, 15 questions per semester. So there's 100 solutions up there posted. Most of them are written by me. That's my standard. So you would like to do what I did. If you don't like what I did, then improve on it. That's your standard. Okay? And a lot of you can do better. Like, I don't have a good spatial sense. I don't go to handwriting. When I look at the best student solutions, they're always better than mine. So you can strive to improve on mine. Does that address your question? Let me just give the converse. The converse is you look at it, you're a genius, you know the answer, you write it down, and you want us to believe you that you didn't copy that from somebody 2 rows in front of you or whatever it is. And it's not supposed to be like that. You're supposed to present the answer and convince us that you understand it. Not only that, you're supposed to convince somebody who doesn't understand the question how the solution is. So yes, the answer is the highest grade possible. Yes?
For one over there, what was the dash pot or the string?
Right here?
Like, yeah, if we had a dash pot, what would...
Let's say we had a dash pot. I think I'm not going to get to Matlab today if I answer that question, and I think probably this question is better than a Matlab question. So let's say it was a linear dash pot. What would FBC be? And I think we'll take this as a learning opportunity. Everybody figure that out, and then we'll discuss it. You want to write it down. You want to write equations on the blackboard in vector form that when you take components or dot products, you could translate into Matlab code. Talk to your friends if you need to.
C times the magnitude of velocity of C minus velocity of B.
Yes? Radius C minus radius B. Over the magnitude, and that's your answer? You put a magnitude here, and this is your candidate answer. F, this was C, this is BC, right? Nice try. Okay, we don't have a lot of time. Yes? No, okay, so let's tell you why you're both wrong, okay? Two smart sounding things. They're both, you have a different answer?
Yeah.
Yeah?
Like BC minus BB without the things. Dot that unit vector. That's the second, and then like times the unit vector again. Or maybe minus the unit vector. I'm not sure which.
Like that?
Yeah.
Okay. Now, why are these two answers wrong? Let's just start with that. Without this absolute value, it's a vector times a vector. What does that mean? It's got to be a dot product or a cross product or something. If you make it a dot product, it's in the neighborhood. But so if you made this one a dot product, then it would be, I think, the right half of this right answer. But then it's a scalar. We need a vector, right? So vector times vector is not sensible. Vector dotted vector is a scalar, doesn't equal a vector. Vector crossed a vector is a vector. Doesn't make sense. This is a screwy direction. What about this absolute value sign? What if the two things are moving in a way, let's say that one of them is still and the other one's moving perpendicular to it, then this thing would be not 0, but the length change would be 0. So like if relative to if you look at the distance from, look at this thing going in circles around this one, the distance is constant, but the relative velocity is not 0. So the absolute value answer can't be right either. So the issue is, can we find the tension in a dash pot? So we're trying to find the tension in this dash pot. What is the tension? It's C times L dot. So that tells us that our answer over there has to be C times L dot times the unit vector in the right direction, which is RBC, divided by the magnitude of RBC. And RBC, remember, the meaning of RBC is equal to the meaning of C with respect to B is equal to RC minus RB. So this is right if we knew what L dot was. So the question is, what is L dot? Okay, and this is a tricky business. I don't know how this guy did it. There are various ways to figure this out. But the easiest way to figure it out is the following. L squared is equal to RBC dot with RBC. Therefore, L squared dot is equal to the time derivative of this, which is RBC dot product with RBC plus RBC dotted with RBC dot. This thing, though, is 2L dot. This thing, it's the same dot product in both of them, is 2 times RBC dotted with the dot of RBC. Cross off this 2 like this, and it says that L dot is equal to RBC dotted with RBC dot divided by L. And you put this all together, and it gives us this thing. So this part here is our L dot. And this is the direction of the force. Now, the guy who figured it out, is this how you did it?
I didn't really, it was less mathematical.
Okay, the more geometrical way to do it is you have an arrow here and you want to figure out its change of length. The change of length has to do with the projection of this distance here. So that's the velocity dotted with this tangent direction gives the change of length, which is probably the way you did it. Okay, any questions about that? I realize that this is like tricky. It's not very straightforward, but if you want to be good at this stuff, you want to be good at this kind of problem.